So hello everybody, this is Rick from Opto Sigma. Just want to thank everybody for joining today. I hope everyone's doing well. As Dan mentioned, I'm going to cover the technical portion of the OptoNano Microsphere assisted microscope. So without further ado, let me just jump into the outline here. So what I want to cover here is just provide, in a sense, baseline. So I think this is what's good to do in the beginning when you're talking about these types of technologies, is to kind of start from the beginning and provide a basis for what I'm going to talk about. So in the outline, what I want to cover is basically the microscope types and their associated resolution. The next thing I want to talk about is the diffraction limit, which kind of gave rise to some of the higher resolution microscopy techniques like super resolution. Now, the next thing is to cover microsphere microscopy, or sometimes called nanoscopy, and then lead directly into the OptoNano itself. And from there, talk about the details and the specifications of the OptoNano microscope. So with that, let's just jump right into it. In this slide right here, as I said, to establish a baseline, I thought it would be a good idea to start with an overview of microscopes and their resolution. So the chart below shows a list of subjects, which are like the ant and the hair and bacteria, along with related feature sizes. And below that, there's a short list of types of microscopes that you'd use to view them. So starting with the human eye, well, it's the one microscope we're all born with, that can see pretty much anything greater than about 200 microns. So to see things that are smaller, like maybe bacteria and cells and things like that, you would then have to transition to a compound light microscope. And with that, you can see things that, well, go down to maybe 200 nanometers. And keep that number in mind because it has some significance to it. So as you go to smaller and smaller things, you get into electron type microscopy, like the scanning electron microscope, which has a really quite a large range from 0.4 nanometers up to a millimeter. You have transmission electron microscopy, which is actually 0.01 up to 100 microns. And then you get into some of the scanning probe types, which are the atomic force microscope, which is really down to the 1 to 10 nanometer range. And then the highest resolution is the scanning tunneling microscope, which gets down to 0.1 to 10 nanometers. So really, really high end. And so you're looking in this range, you're looking at things like molecules, proteins, viruses. Viruses are very significant these days. But the thing I really want to show is of the type of microscopes, there's the optical, which is like the compound light type, and then we quickly go into the electron and the scanning probe. But the one area right here in the middle is the super resolution microscope, and that's kind of what I wanted to establish a baseline with today. So let me move along here. And so what we have is the super resolution microscope and the impetus for its creation. And part of it was, Abbe's resolution limit. And basically what he's saying is that spatial resolution is limited by optical diffraction. And there's a nice equation here, but basically what it says is your smallest feature size, smallest thing you can see under a microscope, is basically half of the wavelength of the light used. So typically for visible light, the smallest thing you can see is right around 200 nanometers, and that's what it said with the compound light microscope. So there needs to be something changed, and this is where super resolution microscopy comes into play. So super resolution microscopy is basically a series of techniques in optical microscopy that allow such images to have resolutions that are actually better than those imposed by the diffraction limit. And there's many examples of super resolution microscopes. So some of them I've listed here. So we have standard fluorescence, we're all familiar with those, but there's quite a few more. There's one called structured illumination microscopy. There's also one called stimulated emission and depletion microscopy, sometimes called STED. There's photo-activated localization microscopy, so that's PALM, stochastic optical reconstruction, or STORM, and then finally near-field scanning, which is NSOM. So now that we've covered kind of the beginnings of super-resolution microscope, let's look into the details of some of these techniques. So here we have a nice table showing many of them. It's ordered by worst to best resolution. At the top, you can see right here, here's a rubric that I've added, kind of identifying the attributes of the numbers. So for resolution, less is better. For some of these other terms, it kind of tells you which is the preferred way to go. So for many of these things, you can see the resolution range. For standard fluorescence microscopy, it's around 250 nanometers, and for near field scanning, you get down to 10. But one of the things that I really want to point out is that there are two columns here, and they're comparing kind of what is needed for the samples. And so in this particular case, fluorescence is required for almost all of these microscopy technologies, these super resolution technologies. Additionally, sample preparation is also required for almost all of them. So that's not a good thing. Basically, as I'm saying by the rubric, having none is better. That's the best way to go. The other thing to look at is image acquisition time. So basically, obviously, less is better. And so for standard fluorescence, for example, it has very fast real-time image acquisition, but some of these other ones can take quite a long time, and that's definitely a disadvantage. Additionally, you have processing right here, image processing. Standard fluorescence doesn't have any, stimulated emission depletion doesn't have any, but some of these do require more complex processing. And the last one, of course, is basically the working distance. Generally speaking, longer working distance is better. So with that, let's talk a little bit about microsphere microscopy. So here we have it. So an optical microsphere basically enables a conventional light microscope to visualize any feature beyond the diffraction limit, and that's what super resolution is. So this is how it works. An optical microsphere is located on the optical axis between the objective and the sample. You can kind of see it right here in the picture. The image process can be divided into basically two steps. So the microsphere manipulates light from the sample and forms a virtual image. And this is the virtual image right here. There's the object. The conventional microscope basically takes over at that point and captures the virtual image. So when you think about it, in the example, if a microsphere can provide a virtual image with a magnification of 4 times, it means that a 100 nanometer feature becomes a 400 nanometer virtual image. So you go from 100 nanometers, the original feature, you go past the diffraction limit, and then you end up at a 400 nanometer virtual image. So what you have then is a conventional optical microscope that can resolve sub-diffraction features by way of magnified virtual image. And that is the theory of how this works. And I want to emphasize this is one of the theories for how the microsphere actually works. So now let's revisit that chart, the table, and I want to pop in OptoMicrosphere microscopy into it and show you kind of where it sits. So what you end up with is you get better resolution in a standard fluorescence microscope, not by a significant amount, but here's some key advantages here. One is it doesn't require fluorescence. 2 is no sample preparation. 3 is it's got very fast real-time image acquisition and no complex image processing required. One of the other issues might be that the working distance is a little on the short side, so it's about 3 microns, but this is something that's not insurmountable. So this is how optical microsphere microscopy fits into the super resolution landscape. So now let's move on to a view here. Here's a review of the advantages of the optical microsphere microscopy. So the advantages are there's no sample preparation needed, fluorescence is not required, It provides real-time images, generally at a lower cost, and improved resolution. And so one of the things I wanted to show here was a comparison of images. And so the electron style of microscopy, of course, as we saw, provides really, really high resolution, down less than 10 nanometers. So this is kind of the golden image right here. But what I want to do is compare this with conventional microscope and images by Microsphere. And the key thing here is that with conventional microscopes, you can look at this and you say, well, in the red circle, there's just one thing there. There's one single feature there. But when you use the microsphere-assisted microscopy, you can definitely tell that it's not just one thing. There are actually 4 different things in that image. And that's the advantage that the OptoNano provides. The graph over here shows price in relation to resolution, and it shows where the OptoNano would sit, basically the microsphere type microscopy. So it's right on the edge of super resolution, less expensive than lower resolution, or I should say higher resolution than traditional microscopes, and better than some confocal microscopes, but of course not as good and not as expensive as the electron type microscopes, so like the SEM, AFM, TEM, and STM. So I just want to show that, I kind of bring price into the picture here because it's very, very favorable from that standpoint. So now let's talk about the OptoNano itself. It's a super resolution microscope, as I've alluded to. Here's the main thing. The OptoNano works exactly like an optical microscope in terms of operation, features, and functions. And it can be ordered with standard objective lenses, from say 5x all the way up to 100x. But one of the things that's provided with the OptoNano is the Microsphere assisted objective lens, and that's included, and that's what's going to give you the ability to see below the diffraction limit, which is 200 nanometers. So some additional features that the OptoNano has is it's got the ability to do autofocus, which is very useful when you're trying to focus in on something that is so small it's a huge time saver. One of the other features is that the software and the motor stages give it the capability to stitch together over 100 images into a single image. That's huge because the field of view with the microsphere is limited, so you want to have a way to get around there and see larger images. And the third one, of course, is they're included with the software is the ability to measure features down to an accuracy of about 35 nanometers. So in a nutshell, that's what the OptoNano does. Let's look at a little bit more detail here. Here's an image. Here's an image with the cover removed. And you can really see how this is put together. It's amazing quality. This is put together with technology developed from Faust technology and integrated by the Sigma Koki group in Japan. They did an absolutely fabulous job with this. It's got clean looks, very nicely put together, excellent quality. When you look at the drawing here, you can see that it's a very, very compact microscope. It's got a height of about 0.5 meter, depth of about 1/4 meter, and about 160 millimeters wide. What I have here is a block diagram showing kind of the internal workings of the OptoNano. So what I want to do is kind of show you from the top down. So from the top, you have the camera. The camera is a 5 megapixel CMOS camera, and it's available either with a color or monochrome. The next thing is the observation unit. And this is rather unique because what it does is it combines the camera with the objective, and it also has a coaxial light interface. So what that does is it folds the light source into the beam path, which is very, very convenient. It provides, in a sense, epi illumination. So, and you can see the LED source right onto the side. Next and below that, we have the objective lens and the turret. And below that, we have some sample stages. So you have a sample stage here. You have an X, Y, and Z axis to control its position. And then another light source down below, which is for the transparent table, so it provides light from below the sample. So in a sense, we have two light sources here. The other thing we have two of is z-axis motorized stages. So you have one on the sample stage here, but you also have one on the focusing stage. So there's one that adjusts the focus for the objective, and then there's also that adjusts Z position for the sample stage. All of these have their own power supplies, of course. You also get the motor controller right here, the stage controller, and its power supply. And of course, you get software to run everything, as I showed before. Now, here's some of the main specifications for the OptoNano. One of the nice features here is the observation conditions. Yep, no special preparation, it's just air. You can do everything in air, no vacuum required, no dyes or anything like that. So that's a real advantage. The illumination wavelengths is you can get monochrome. This one is 460 nanometers blue, or you can get another version that's white light, which centers around 700 nanometers. But the lenses, you can get a 10x standard microscope lens, but also you get the OptoNano 200 lens, which is a Microsphere assisted objective. The working distances on the shorter side, 0 to 3 microns. Limit of resolution, 200 nanometers, as we talked about, but the effective resolution based upon the wavelength of light, for the monochrome, it's 137 nanometers, and for the white light version, it's 154. Last item here is the lens turret. It has 4 holes for manual revolving of the objectives, and the spacing, of course, is 90 degrees. Now here is an image of, it's basically the user interface for the microscope. This is the software. And so I just want to kind of show you some of the buttons and how it's laid out, and kind of an indication of some of the features and benefits of the software. So up at the top, you have control for the image. You have look at a live image, you can capture the image or take a quick snapshot. It also gives you selections for the type of objective you have, and also, of course, the OptoNano lens itself. There's a key item or key set of buttons right here, and these are some of the really unique features. First, as I mentioned before, there's the autofocus function. Then also there's the ON focus, which represents the focus for the OptoNano lens, has a little bit of a different algorithm, different routine. And then this other one right here, it says stitch, and that's what allows you to stitch together multiple images to create kind of a wide field of view final image. So the main image here is what you see on the screen, kind of guides you to the features you want to look at. And then down below, you have a gallery of the images that you've taken, so you can pick from those very quickly. The rest of it, you have camera settings, so you can do auto exposure and auto gain, along with white balance. And then down here, you have an ROI screen. So once you have identified the feature you want to look at, you can basically surround it with a circumference or a square, and that'll tell the software to hone in and scan in these particular areas. Below that is the motor controls. So you have the sample stage right here. So you have X, Y, and Z and home. And then you have a single axis for the body, and that's simply to control the focus of the objective. You also have coarse, fine, and extra fine position control, so that you can, once you get down to near where your samples are, you can adjust it to a very fine degree of freedom. So that's it. That's the software user interface for the OptoNano. Now what I want to do is kind of talk a little bit about the images that you can get and what it really looks like with the Microsphere. So what I have here is a shot of kind of pre and post Microsphere images. And what you have here, you see there's definitely a resolution test target here. You can see the bars very clearly. And the item in the red circle, that is the Microsphere itself. And it looks kind of strange a little bit because it doesn't really seem like it's doing much, but it will, as you'll see. And this black portion right here, this is actually the support structure for the Microsphere. So that's what's attaching it to the objective itself. So now you go over to the right, and once you do the focusing of the nanosphere, you start to see the images right here. And here's the image seen through the microsphere. And this is what gets you past the diffraction limit and what the software can actually stitch together. So it's a very limited field of view right here, but with the stitching software, you can get much, much wider fields of view. So that's what the images look like from a microsphere standpoint. Now here's another one. Here's a comparison of other images taken. This is a semiconductor chip. And so, you look at these images and they look pretty much the same. You can see the lines here. Maybe the one taken with the microsphere looks a little bit better. It's a little bit cleaner. But the area that I really want you to focus on is the area in the red circle. And when you look at that, that's where the differences start to come into play. So let's take a closer look here. So here now, when you take an actual closer look of those two images, you really see that the image on the left, you can't see the line pairs. They're kind of mushed together. And this is the result of the diffraction limit. But when you look at the image from the OptoNano, you can clearly see the line pairs. And this makes a difference. This is similar to the image we saw in the previous slide, where you saw the four spheres clearly with the OptoNano, but in the standard light microscope, it looked like a single feature. And so the OptoNano really had the resolution to distinguish those individual items. So let me just go over a recap of what we talked about. So first, as we talked earlier, there are many different types of microscopes, and their main differentiation is resolution. And so we said for light microscopes, the diffraction limit is the best resolution, which is about half the light's wavelength. Then we talked about super resolution microscopes and breaking the diffraction barrier using different techniques. And the microsphere was one of those, and those provide super resolution capability with advantages over other super resolution devices. And one of the things we talk about is sample preparation and no fluorescence and instantaneous image acquisition. And so what this is the introduction. We'd like to say this is the introduction of the OptoNano. It is a microsphere-based, microsphere-assisted super resolution microscope. And like I said, we are releasing it now. OptoSigma is releasing it right now. But what I'd like to do now is let's take a look at the OptoNano, something more close up. Let's look at the real thing and go through an actual demonstration. So I'd like to pass you now back off to Dan. And Dan, why don't you take over from here?